Hello again, AP Calc AB students. Mr. Rector from Avon High School. We're going to take a look at our second video that covers topic 7.1. We're modeling situations with differential equations, and we've got three really quick multiple choice examples here and combination of free response examples to take a look at. So let's get to it. So we're going to start with our example 3 here, never stop learning. And this is an actual, it's a famous learning model. I believe it's called the Ebbinghaus model, if I'm not mistaken. But it says that the learning rate for a skill S is proportional to the difference between the maximum potential for learning that skill M and the amount of that skill already learned L. Write an equation that models this relationship. Well, the very first thing that you want to do is start whittling away and find the very important pieces of language that you can translate into mathematics. So the very first thing that you want to notice is you've got this phrase learning rate S. And that's very, very, very important because you need to equate that to a derivative, the rate of S. So that will just be ds over our dt. Now, the fact that it says is proportional, that's the next piece of information. Remember from our previous video, we had a quick little refresher about directly proportional versus inversely proportional. If you don't see an adjective in front of the proportional, the assumption is that it is directly proportional. It varies directly. So what that means is that you take your constant of proportionality, which we typically will use k, and you will multiply it by what's to come up. The difference between, well, that seems pretty logical that you're going to subtract a couple of things. We probably need to put that quantity in parentheses then. Between the maximum potential for that skill, M, and the amount of that skill already learned, L. And so I'm going to call that M minus L. Now, if you're wondering, how do we know which one goes first? That's a great valid point. To an extent, it may not matter so much because that would only affect the value of K, as in we could factor out a negative to get whichever order of M and L that we wanted. So I wouldn't worry so much about that right now at this point. Another thing that kind of bothers me about this question is that the rate at which one is learning is basically it's inferred that this is something that's decreasing because as time goes by, you're basically forgetting something, kind of like being in your calculus class sometimes. So really, this K should be a negative number. And a lot of times it's best to kind of denote that. Now, I know that K isn't declared, so it could be negative or positive. And what I mean by that is if we wrote it like this, then it's very likely that the K value itself is going to be positive so that I can actually have this negative relationship here. If I write the problem like this, then it's very likely that the K that I'm going to end up computing is going to be negative already. So don't worry so much about that. I didn't give you any directive about what K had to be from a sign perspective. So there's nothing wrong with that first answer, but I would take the second answer as well. All right, let's take a look at example 4. An IV drip administers medication to a patient's bloodstream at a rate of 3 cubic centimeters per hour. At the same time, the patient's organs remove the medication from the patient's bloodstream at a rate proportional to the current volume V of the medication in the bloodstream. What equation describes this relationship? And we're back to multiple choice here. So again, I don't want to attack this really any differently, even though it's multiple choice. So I want to think about, we've got the IV drip administers medicine at a rate of 3 cubic centimeters per hour. Okay, well, that's good to know. The patient's organs remove the medication at a rate proportional to the current volume V of medication in the bloodstream. So really what we've got going on here is a rate of change of the volume of this medicine in the person's bloodstream. And that's really good that all four choices show dV/dt on the left side, because it wasn't really clear initially that that's where we were going. It jumps right into what's going on the right side. So we know that this rate is changing by a constant of 3, because that's the amount that's going into the bloodstream. But then we have this outward that's proportional to the current volume V. Well, this proportional is implying direct proportional, and N is always going to subtract out. It's always in minus out, and that is going to lead you to this answer, A. Now, the problem with B is that we don't really get this in and out. This is more of a -3 times K directly proportional to V. We notice that C is kind of in the ballpark, but the K and the 3 are just kind of in the wrong spots. And D is really bad because it's introducing this variable X that isn't really defined or even discussed in the problem whatsoever. All right, we have one more problem to do. It's another multiple choice. It says a chemical is diluted out of a tank by pumping pure water into the tank and pumping the existing solution out of it. So the volume at any time t is going to be given by 20 plus 2t. The volume is given by that. I might even want to call that the volume. Get a little closer there. The amount Z of a chemical in the tank decreases at a rate proportional to Z and inversely proportional to that volume. So we notice that each of the four answer choices begins with a dz over dt, which is what we want. That's good. Proportional implies directly proportional. So we should have a k times z in our answer. And really, we notice that only two of these really demonstrate that. Choices A and B seem to still be on the table. But the inversely means that you're going to divide. So you have in the denominator what follows the word inversely proportional, and there's your volume again that relates right back to this 20 plus 2t. So we should see that 20 plus 2t in the denominator of the k times z, and that's going to be your answer. A lot of these problems are going to be written a little bit more consistently. When we get to the place in this unit where you have to write your own differential equation and then solve it, they're not going to be quite as varied as these examples. These examples can be pretty tough to set up. I just wanted you to watch this video to kind of get used to some of the language that's being used so that when the time comes to apply this to a real world problem, which is in topic 7.8, things will be pretty ready for you. From this point forward for the next several topics, you'll be given the differential equation and be asked to do some things with it. Hopefully this helps. We'll see you next time.